Okay, last time I left off talking about the amount of energy associated with one quantum action of rotational energy, kinetic energy, which is right here, one action quantum of vibrational energy of each type, bending, symmetric stretch, and asymmetric stretch. And all of this is compared to the thermal energy at 300 Kelvin, which is Boltzmann's constant times the temperature. Now, I make no guarantees that these equations for rotational and kinetic and linear energy are correct. They were derived from several bold guesses that I may later find to be incorrect. And even if the bold guesses were correct, a miscalculation in the mathematics could make the numbers incorrect. In fact, I'm so familiar with my bold guesses being incorrect that I made this my Facebook status yesterday. I pride myself on my ability to guess incorrectly about things that most people don't even know can be guessed about. Yet this is, I think, the key to the scientific method. You have to permit yourself to guess, and sometimes guess incorrectly. Some will call it speculation, because often these guesses about reality are phrased in the form, "This is the way it is," where the guess should be phrased, "Is this the way it is?" But in the absence of evidence guiding you one way or the other, usually we tend to forget which of our hypotheses are still just guesses, and which of our hypotheses have gone through the rigors of testing. Okay, my bold statement earlier was that a quantum of action, and that is actually a known quantity, 662.6 atto-joule seconds, that's 10 to the negative 36, 662.6 times 10 to the negative 36 joule seconds. It's essentially like a little dart. We're throwing at a dartboard that represents all of the available modes of motion of the carbon dioxide molecule. Now the dart can only go into one region of the dartboard, meaning usually it will either affect the translation or the rotation, but not both. Again, a bold statement, but the next one is even bolder. So, the area of each section of the dartboard is proportional to a quantity that is derived as follows. Number 1, divide the minimum action of the mode by the thermal energy. That is E mode divided by K sub B T. That's Boltzmann constant times temperature. Number 2, take Euler's constant to the power of that quantity you just found, to the power of the negative of that quantity, and then multiply your result by the degeneracy of the mode. The translational mode has degeneracy 3 for the x, y, and z directions, and the rotational modes have degeneracy 2 for rotation and precession, I think. I mean, I know that there are 2 degrees of freedom associated with rotation, but I just don't know if the second one is properly referred to as precession. So here is my code for calculating the rotational energy, the linear energy, the bending energy, symmetric energy, and asymmetric energy for the carbon dioxide molecule with oxygen atoms on the sides. These are also bold statements because I put together the derivation completely on my own. These are not so bold because I'm using numbers that are pretty well known, that the energy of a photon is h times c times the wave number. So now I'm going to generate a list of exponents for the rotational energy, which comes to be negative 0.07, the linear energy, which is teeny tiny number, the bending energy, which is negative 3.19, symmetric energy, negative 6.65, and asymmetric energy, which is negative 11.265. Then I'm going to take e to the power of those exponents, and you'll see this is representing the occupancy rates. So about 92.89% of the available rotational states are rotating, so that's these. 99.97% of the available translational states, 99.9661. So everything, all except 0.03% of the carbon dioxide molecules are moving, essentially. And 4.08% of the available bending states are bending, so that means that about 4.08% of them would be basically in the process of emitting in that 1500 or 15 micrometer line, or the 667 per 667 per centimeter. About 0.12% are available in the symmetric stretch mode, and 0.0012% of the available asymmetric stretch states are oscillating. So what this degeneracy refers to is how many available rotational modes are there. And there are going to be, for every 3 rotational states, there's going to be for every 3 translational states, there's going to be 2 rotational states. And I don't know for sure, but if visualization is any kind of tool here, sorry, that's the wrong slide. I would say there are 2 degrees of freedom. You can bend left and right, or you can bend up and down. So there would be 2 dimensions to bend. And then there's just going to be 1 dimension for asymmetric stretch and 1 dimension for symmetric stretch. So to go from relative occupancy to energy distribution, we have to multiply the occupancy levels of each of the state by the number of modes in each state. Okay, so each mode of motion is either activated with minimum action h, or it is not activated. And the probability of a mode being activated is equal to this quantity over here, e to the negative e over kt. When I calculated the probabilities of each mode being activated, e to all of those exponents, negative e to the kt, I got these occupancy levels. But to find the area of the dartboard, the respective areas of the dartboard, I'm going to take these, not the energy levels, those occupancy levels, and multiply by the degeneracies. The degeneracies are just 2, 3, 2, 1, 1 for rotational, linear, bending, asymmetric, and symmetric. Now when I multiply those occupancy levels times the degeneracies, I get the relative areas of the dartboard. That is, for any given quanta of energy, what's the relative chance that it will go into each mode of motion. For instance, the linear mode has an area of 2.99898 units, almost 3 units, while the rotational area has a relative area of 1.85782 units, which is almost 2. Now that brings us to the partition function. The partition function is the sum of the relative occupancies. 1.85782 plus 2.99898 plus 0.081616, etc. Now, I probably wouldn't call this thing the partition function if left to my own devices. I'd just call it the total area of the dartboard. But that's not a very good description either, because it's not really a dartboard. Calling it the partition function, though, does kind of force us to search for a better mental description. The dartboard is the space of kinetic energy storage modes. Kinetic energy storage modes of a carbon dioxide gas. What is an energy storage mode? In turn forces me to consider what are the units on this quantity, and I think the answer is degrees of freedom. This is the same unit you would have on the degeneracies, because there's 2 rotational degrees of freedom, 3 translational degrees of freedom, 2 bending mode degrees of freedom, 1 asymmetric stretch degree of freedom, and 1 symmetric stretch degree of freedom. And so the partition function would be measured as 4.93971 degrees of freedom after it's taken into account that only part of a degree of freedom is occupied here, only part of a degree of freedom there, only a part of the degree of freedom there, etc. Okay, I calculated a couple of other things here. The portion occupancy should be the portion of internal energy U that goes into each mode of motion. So if you've got internal energy of 1 joule, then 0.607 joules would go into linear kinetic energy, 0.376 joules goes into rotational kinetic energy, and about 16.5 millijoules would go into the bending vibrational mode. And the thermal occupancy is the portion of thermal energy that goes to each mode. Okay, so if you calculated PV equals nRT, the value of PV is in joules. If PV is joules, then there would be 1 joule in the linear mode, about 619 millijoules in the rotational mode, and 27 millijoules in the bending mode. So right now I want to do a reality check. Did I get anywhere close to a result that we should expect? And I'm afraid at the moment I have to say no. So using the degrees of freedom I calculated, 4.9397, also known as the partition function, and treating it as degrees of freedom, I can plug it into a fairly well-known equation for the specific heat at constant volume. The value I got was around 20.5 joules per mole Kelvin, somewhere around 5/2 times the universal gas constant. And this is a far cry from the experimental specific heat at 28.2 joules per mole Kelvin of nearly 7/2 R. In particular, if these occupancy levels for rotational, translational, and bending modes had been around 100%, 100%, 100%, and these other levels had stayed as they are, then our partition function would have come out to be 2 plus 3 plus 2 equals 7 instead of 4.93291. And our calculation would have come out very near the experimental value for carbon dioxide's molar specific heat at constant volume.